So good afternoon, everybody. Welcome back to lecture number what?
17.
I think it's 17, yeah. Lecture number 17. Today, let's revise it a little bit. I'm going to give some comments about the previous figure, which is this figure. So the equation here, power air gap equals I2 squared times R2 over S. Is this per phase or per three phases? It's for one phase. If you want to do the three phases, you have to multiply it by 3. This is very important, okay? So you can put the 3 right now in your notes. In the example, there is 3. Clear? Clear? So, what we call about anything before the air gap, the losses are occurring in the stator itself. After the air gap, the losses are occurring either at the rotor or mechanical losses, or no, we call them rotational losses, which is mechanical, but I call them rotational losses. The most important equation is the air gap. You can find the air gap power, which is the power that crosses the air gap, to be 3. So let's add a 3. Let's add a 3. 3. I2 square R2 over S. Now, then this power splits into P2 and P converted. What's the other name of P converted?
Mechanical.
P mechanical, which is the power that's converted from electrical to mechanical. This is the power that crosses the air gap. تمشي بالهواء. This is the power that gets materialized as mechanical power, which has also stray and windage and friction losses. We call all of them as rotational losses. And then you get your output power. Keep in mind, in the mechanical side, we get torque induced omega mechanical, here torque induced omega synchronous, here a torque friction omega m, here torque load omega m. Okay? Keep in mind also that there is a shortcut to find P converted or mechanical power. Just multiply the air gap by 1 minus S. What does that mean? It means if I change the speed of the machine, the converted power to mechanical energy, because if I change the speed, slip will change. If I change the slip, the power that's converted to mechanical would change. Now, given that the speed is changing, we may also have a change in the torque induced. Okay? So when you control the machine, which is one core concept, you will find the term 1 minus S very common. Okay? In the last lecture, we solved this simple exercise. Now, in the major exam, we will have induction machine in our major exam. But I'm not going to ask this question because this is E360. This is it's a repetition of E360. What's the slip? What's the mechanical power? You add them with the windage and friction. And then what's the air gap power? And then you do the copper losses, which is S times the air gap, which is the converted power 1 minus S. So this is just a quick example to get familiarized with the energy flow. For the equivalent circuits, I told you I like this circuit the most. The second circuit that I like is the one where you move the branch here. Is the one, what is the original circuit? We don't have the exact. This is this circuit is also useful where you put R1 here and you put the parallel branch here, because you will have I1 to be I parallel plus I2 prime, and we will solve an example using this circuit. Okay? The torque speed characteristics. Torque speed in terms of stability, once you turn on your machine, you should really operate it at this linear region, at least this linear region where you have the stable region. Anything unstable, you're allowed to operate only during transients. So let's think a little bit. Let's think about why this curve is important. First of all, is this curve always fixed, or it varies for every machine? So there is 4 classes of machines. Class A, B, C, and D. This is additional information. So in industry, when you buy any machine, you have to check the classes for induction machine. So if you look, for example, classes of induction motor or machines, so this is a very interesting curve. This is not required, it's for your own knowledge, but I think it's very useful. So if you look at this curve, for example, this is torque speed, صح? Class A, what do we notice? We notice it has high maximum torque, and then the slope is higher. There is a class B which is normal. Class C, starting torque is higher, is the maximum torque. Class D is similar to class D, but it overshoots a little bit. Unless, what's the default class? A or B? In industry, A or B. What applications you need class C or class D? If you require high starting torque from the beginning, you have, for example, a crane hoist. وش الهويست؟ بكرة، صح؟ البكرة. Hoist. So for hoist application like elevators, most likely it's class D or class C. Get it? So if you get stuck in the company, you don't know, just say class B, okay? It's class B, average, okay? Class A is a little bit more detailed. Now there's other information that talks about classes of induction machine. Here is where they're used. So they vary in the slip, etc. But if you get for class B is pumps and fans, class C crushers, steering machines, compressors. Class D is for oil application, oil well pumping, the pump, cranes, elevators, high starting torque. So Aramco maybe is buying lots of class Ds. Class A is powering of injection molding machine. This is one of the applications. Keep in mind the main difference is the starting torque. Maybe the slip a little bit, but starting torque is what pretty much the peak where it's located. And in this course, EE 462, when you design the machine, you have to pick the class. In other words, you have to change the starting torque. And how do we change the starting torque? The starting torque is last lecture we found the equation of torque, then we decided to find the maximum torque. This is from EE 360. This one is also from EE 360, and now here we're dividing T over T, 2T max. We want to get something like the transfer function for 380 or 207 by writing it as system level. So if you substitute A to be R1 over R2 prime, what is R2 prime? It is the resistance of the rotor reflected to the stator side. And how to do reflection? Multiply by A squared, which is the ratio of the windings, N1 over N2. If you do the equation, now why do we do these ratios? Is, for example, if you have a curve, say this is class B, and let's say we want to compare T max with maybe a point T. Now here we divide it by 2, and don't quote me, I could be wrong, is to get rid of this 2. So if you multiply by 2, this 2 will be gone. لأن في regular torque ما في T. This is just a trick. So you're comparing them, half of the torque to the maximum torque. So instead of maybe half, you get 0.25. Now what you need is you need these ratios so that you can plot versus a slip. Now, what he did here is he found this expression. You can have this, you can have that. Here you have slip. So if you change the slip, how much you need to change the slip to get a ratio between T and half of T max. Remember, this two to make the math easier. Now, it turned out to comparing currents of two operating points at the same torque and speed center to center, you would have T1 over T2. You will divide the ratios of the current squares times slip of 2 over slip of 1. From where we got this? We get this from the air gap equation. For the air gap equation, if you notice, it is I squared over S. Now, I2 is proportional to I1, which is the stator current. So, doing some maths, you would note that the ratio between the current at machine 1, this one is not rotor or stator. This is machine 1 and machine 2. So 1 is IM1, IM number 1. 2 is for IM induction machine number 2. So I'm dividing the two ratios between each other. Clear?
Yes.
So if I divide the current, I need to have S2 over S1. This is one ratio. Now let's get rid of R1. If you get rid of R1, you would have maximum slip at R2 prime over X equivalent. Now the torque max would become a simplified equation. If you repeat T over 2T max, you should get a simpler expression. S times slip, which is the slip of the machine operating at slip S. Slip max over slip max squared plus slip squared. Again, if you compare the two currents for machine 1 and machine 2 and add the maximum, or I'm sorry, this is slip 1. This is slip at certain speed and another speed for the same machine, not different machine. If you want to add the max, then you reach this equation. We will use these equations when next week, okay? Or maybe Thursday for the control. So these equations, 4 and 5, as well as this 4 prime and 5, they are important, okay? Now here we're using the approximation A equals 0 because R1 is 0. So let's run this quick example. Let's try to solve it real quick. A 3-phase induction machine, 460 volts, that's line to line, 740. So what's the slip? What's the slip? Calculators. 1800 minus 1740 over 1800. So the slip is 0.033, right? So sometimes he tells you without telling the speed, this is the operating speed or rated speed? No, that's rated. لأن ذكرها في البداية. These are nameplates. Okay? 60 Hz 4-pole wound rotor. So what does he mean by wound rotor is the rotor bars or the rotor windings are short-circuited. So we have slip rings. Induction motor has these parameters. We have R1, R2 prime, XM, X1, and X2 prime. The rotational losses, which is stray and windage and friction, rotational is 1.7 kilowatt. With the rotor terminal short-circuited because it's wound rotor. Find starting current when started direct on full voltage. So what will happen if I connect the full voltage, 460 divided by square root of 3, I want to calculate the starting current. So how to solve this equation? I'm using, this is the exact circuit, I don't have RC, and I'm moving the parallel branch ahead of R1 and X1. So this would make my calculations faster because I can calculate I1 to be the magnetization current plus I2 prime. This is EA360. We're taking 462. I wish I can solve it, but we really do not have time. If you have questions, let me know. It's 460 over square root of 3 divided by J30. This is J30. Plus 460 over جذر 3 over 0.2 over 1. Why did I put 1 here? Because starting torque slip would equal to 1. This is R2 prime over 1 plus R1 plus J.5 plus J.5. Each one is J.5. So what do you note here, the I1? It's 250 at an angle of minus 66 degrees. So 250 amps is too much current. The second part is, he's asking you what is the starting torque. To calculate the starting torque, I need to calculate the air gap power over synchronous speed. Here it's a 3 I2 prime. I already have, this term is I2 prime. I plug it here, R2 prime over 1 divided by omega S. What is omega S? Synchronous speed. Convert 1800 RPM by multiplying it by 2 pi over 60. Do you remember this equation? Same. So if you do the math, you should get 242 newtons. If you do the math, you should get 186 newtons per meter. Keep in mind, what's the magnetization current? It's 250 angle minus 66 and minus 242, which is roughly 8 amps, right?
Yes.
8 amps at an angle, at the same angle. No, I think it has a different angle. I think it has 90 degrees or whatever. Now we're done with part A. Part B, now we got rid of the starting stuff. Now we go to the full load. Full load, it means I change the slip from 1 to 0.0333. So what is the full load current? To calculate the full load current, I need to first get the slip. Actually, he's asking what is the full load slip first. And then what is the full load current? Full load current is Im. The same story, you repeat the same equation. The only thing you change S from 1 to 0.033. It is your job to do these calculations at home. We're going to have, maybe we will have this question in the major exam. Maybe, I don't know. So please make sure you do the equations. And then the third equation, the third question, find the ratio of starting current to full load current. This is a common thing. For DC machines, the ratio is twice. For induction machine, the ratio is 5 times. For synchronous machine, what's the ratio?
1.
Synchronous machine is always at synchronous speed.
Yes.
So the ratio is 1. Doesn't change. It's question in the exam. So remember these numbers. These numbers are not in the slides, but these are industry standards or rules of thumbs. So for IM, the ratio of starting current over full load, roughly between 5 to 7. For DC machines, the ratio starting torque over I full load is roughly maybe 2 to 2.5. Okay? So when you design your machine, if your starting current is 10, that's a problem. It's over, basically something is wrong in your design. What is the problem of the starting current? When you connect your load, it will draw so much current that even surrounding loads may experience sudden drop in the voltage. That's why when you connect, when the AC in the summer kicks in the compressor, you get light dims because the starting current of the machine is very high. Okay? This is very important. What else do we have? We still have to find the ratio between them is 5.66. That's within the range, so that's nothing is wrong with that. Find the full load power factor. Here the question is find the full load power factor. Basically, it's cosine of 0 minus the angle of the current. What is the angle of the current? Keep in mind the angle of the current here is 20 degrees, so it is 0.936. However, what is the power factor at the starting torque? It's cosine of 66, which is roughly 0.4. So at starting torque, we have low power factor. When we reach the full load, we have very nice power factor lagging. Okay? For the synchronous machine, what is the power factor? Depends on the field. It depends on the armature current. So you can see the power factor in synchronous machine, it spans from lagging or leading, but for induction machine, it starts at low lagging up until it reaches at full load, high lagging. It will never ever be leading. Okay? مرتضى هل الكاميرا تصور؟
Yes.
Okay. What else do we have? I'll take more time. If you want to leave, you can leave. But I have to finish this because this is E360. We want to go to 462. And you cannot understand unless I do this revision. The other question, which is very important question, is find the full load torque. The full load torque is again the air gap power at a different slip over synchronous speed, but you still need to calculate I2 at full load. What is I2? It is this term. So this term. If you don't have time in the test, just put 44 and move on. Who cares about 3 amps, okay? You can approximate anything. You can ignore the parallel branch if you don't have time. Maybe you'll get 8 out of 10, but it's better than 0. So you can approximate 41, whatever. I think the angle here is wrong. I'm not sure, but let me know if it's wrong. Could be wrong. The maximum torque, if you plug the numbers, is 176. So if the maximum torque is 176 and the starting torque is 186, do you think this is a class B machine or more like class C?
What was it?
Class B.
D.
This is A or B. It is A or B. But it's somehow B, but it's more close to C and D. Because this is the starting torque is 180, and then the full load torque is what? 186. So it will start, peak, and then go to. So starting they are a little bit high. I think it's more like class. I think it's more like class B. Class B. This is a class B machine. The other question that he wants you to know, and this is probably it was not explained in E360, is calculate the internal efficiency. So what is internal efficiency? Internal efficiency is the efficiency of the internal mechanical electromagnetic conversion. Basically, what it only asks about, if you go to the curve, the internal efficiency is the ratio between P converted over air gap converted. So think of this as a subsystem. I don't care about stator, I don't care about mechanical, I just care about internal here. What gets converted from electromagnetic through the air gap to what gets converted to mechanical, which is 1 minus S. It's easy. That's why we like internal efficiency. This is an easy way to estimate the efficiency of the machine. It's just 1 minus S, because usually core losses and these losses are not much, but rotor loss is somehow significant many of the time. So if you say, what is the internal efficiency of your machine, you will notice that it is internal efficiency is 1 minus the slip, which is 96%. So what is the overall efficiency of the machine? Again, it is P mechanical minus rotational over the input power, because it's P output over P input. What is P output? It's P mechanical minus rotational, because we have mechanical, it's 1 minus S air gap. Rotational is already given, 1.7 kilowatt. So what is 1 minus S power gap minus 1.7 kilowatt over input power? Keep in mind we put the power factor here, don't forget it. So it's 87. So clearly internal efficiency is 10 points high than the actual efficiency of the machine. Part C is the slip at max. You plug the number. This is covered in E360. Maximum torque is 438. And then the last question is not covered in E360, which is how much resistance should be added to get the machine maximum torque occurs at start. Basically how to make it from class A and B all the way to class C and D, to be specific, class C. The only thing is in this part, which is the last part of our revision, is you have to adjust R2 prime to R2 plus R added, and then you equate them. You make this at 1, you equate them, square root of them, solve for R added, which is 0.8 ohm. So now, can I change the class of the machine by adding an external resistance? Yes. So external resistance is the first way to control the machine by changing the starting torque from low to high. So if you have an elevator and you have a class B machine, what should you do? External resistance. Add external resistance. Okay? With that, we finished the first set of slides talking about introduction to induction machine. And if you have any question, do you have any question?